We're going to take a look at the objectives here before we get started. Along with those two agree-disagree statements, you should also be watching for these while we take the notes. We're going to be trying to explain what a simple machine is, so you're going to need to be able to give a definition for that vocabulary word. Okay? Then you're going to need to be able to explain how machines affect the strength and the direction of forces. So in some way, they're going to impact those. There's going to be an effect on the strength of the force. So is it stronger, weaker? And there's going to be effect on the direction of the force. Okay? And then you're going to need to be able to describe how machines make work easier. These two are connected. Okay? So something about how it affects the strength and direction of the force affects how it makes work easier. And then lastly, you're going to need to be able to calculate efficiency. So there's a formula coming at you this chapter, or this lesson specifically. Okay? Beginning with machines. Machines are designed to transfer mechanical energy from one object to another object. Okay? We learned in the previous lesson that when you do work, you transfer energy. So the fact that there's energy being transferred here lets us know that there is work being done. So anytime you're using a machine, you are doing work.
Isaac, move your big head.
There are two types of machines that we're going to discuss today.
Preferably out of the way.
And we're going to start with simple machines. So simple machines are machines that do work using one movement. So we already know the answer to one of our agree-disagree statements, right? Simple machines are in fact machines that do work using just one movement. And we're going to look at a bunch of examples of those. We're going to talk about 6 different types of simple machines. So remember I said we're talking about 2 different types of machines, and then so the first type is simple machines. We'll talk about 6 examples of simple machines, and then we'll talk about the second type of machine. So the first of those 6 is an inclined plane. An inclined plane is a flat, sloped surface. So an example that you have probably experienced is a ramp. You have a flat surface that slopes from a low level to a high level. And what this does is it changes the distance over which the force is applied. So it's not affecting the direction of the force. It's just affecting the distance that it acts over. I want you to take a minute. I want you to turn to somebody next to you, and I want you to remind them how we calculate work. So, together we pieced out that work is equal to force times distance. Okay? If we wanted to write that equation out like this, it would help if I wrote the right letters. Times distance. Now, remember we just said a ramp increases the amount of distance, but the amount of work stays the same. So, if the amount of work stays the same and the amount of distance increases, what's going to happen to the strength of the force required to move this object?
Bigger, smaller.
It's going to decrease. It's actually going to get smaller. Okay? And you've probably experienced this. If you've ever had to lift heavy bags up a distance off the ground and put them onto a ledge, it would be easier if you could just slide those bags along a ramp, right? Than to just pick them up. And that's because you make this work easier by changing the amount of distance. Because a greater distance means you have to put in less force to do the same amount of work. So a ramp is going to make work easier for you. It increases the distance you have to travel, but you don't have to use as much force. Let's talk about the next one. A screw is an inclined plane that's wrapped around a cylinder. So the most obvious example is one that you have experienced if you've ever tried to join 2 pieces of wood together. Okay? And that's an actual screw that you might use in woodworking class. Another good example is a bottle cap. Anything that's got those grooves on it so that you can screw it together. And the way that a screw affects your force is it takes the straight line force that you put on the object and causes curved motion. So instead of having the object move in a straight line, even when you apply a straight force, it can cause it to curve instead. Wedges are inclined planes that move. And sometimes you can think about it as like two inclined planes that meet. So for example, a knife, right? A knife tapers to a point, correct? So it's like two ramps that are sandwiched together. So a wedge is this inclined plane that you can then move. And how a wedge affects force is it changes the direction of the input force. So if you have a thing that you are cutting, you push down with your force, but the knife pushes out, which is why that substance you're cutting actually separates, because the force pushes it away from each other. So you put force in the down direction, and the wedge changes it to a force that pushes out. And then we have a lever. A lever is a simple machine that pivots around a fixed point. Good examples of these are bottle openers or seesaws, or you might have heard them called teeter-totters. Okay? These change the direction of the input force, and they can change the strength of the input force if that lever is strong enough. Let's take a look at how this works. So if I have a bottle and it has a bottle cap on it, and I'm trying to take that bottle cap off with a bottle opener, it's going to hook around here. Okay, there's my bottle opener. So notice right here, this is our fixed point. This part of it is not moving, right? Where it attaches to the bottle cap. Okay, I'm going to push down on this side, and the bottle cap is going to pull up on this side and pull the bottle cap off. So notice how it has changed the direction of the motion. Okay. Now, what if this bottle cap really doesn't want to come off? Well, I can make this easier for myself if I have a longer lever. I'm going to try and move this drawing around. Maybe not. We'll just erase it and I'll draw it again down here where you can see it better. You have your bottle cap and you need a longer lever. So what's happening when I use a longer lever right like this, okay, is this distance that the lever moves is really big, right? And this distance over here that the lever is going to pull up is going to be significantly smaller, correct? So my force that I put in can be smaller because I'm moving at a really long distance, and then because it moves at a short distance on the other side, that output force is greater than the force that I put in because it moves at a smaller distance. So by changing the distance that I have to move this, then I change the amount of force I have to put in. Next up, we have the wheel and axle. This is a shaft that's attached to a wheel that is larger in diameter so that they both rotate together. Okay? If you've ever seen a wheel of a car and the axle that is attached to that wheel, you'll notice that the axle is significantly smaller in diameter than the wheel is, correct? Another good example is a screwdriver. Again, you have the actual metal shaft of the screwdriver is much smaller than the handle of the screwdriver. And that is not just so that you can hold on to it easier. It actually has a mechanical purpose. And that's because this is going to change the distance that the force is applied over. So just like with the lever, making the lever longer changes the distance, having the diameter of the handle be larger means that you move it a larger distance. So think about it. If I've got this big handle, okay, and I turn it a significant distance, then the smaller one is going to turn a smaller distance again, and as a result, I don't have to put in as much force on this one to get a larger output force over here. Okay? Again, it's making work easier for me by changing the distance that it moves it. So it means I require less force. And lastly, we have a pulley. A pulley is a grooved wheel with a rope or a cable wrapped around it. For example, the rope that pulls a flag up on a flagpole. This is going to change the direction of the input force. If I pull down on the rope, the flag goes up. So it's changing the direction of the force. And it also changes the force required because there are more ropes supporting the object, especially if I have multiple pulleys in a system. That changes the total number of ropes that support the object, and as a result, I don't have to put as much force in. I want you to notice that for all of these simple machines, they do one motion, right? That goes back to our definition of simple machines. They do work in one motion. Next up is the second type of machine, and that is a complex machine. A complex machine is just a combination of two or more simple machines that are working together. So, for example, a bicycle is a complex machine. A bicycle is made up of a pulley, so the bike chain is a pulley. It's made up of pedals. You have wheel and axle, simple machine working at the pedal level, and then the handlebars of a bicycle are actually levers. So, all of these simple machines together make up one complex machine. Let's talk about machines and work. Machines do not change the amount of work that was done. Okay? So the amount of work that I put in is not changed by the machine. It's not magnifying it and adding to it. It's not subtracting from it. The amount of work is not changed. But machines can change the distance of forces applied over, so they can make that input distance larger. They can change the amount of force necessary to do the work. So what they will do is they will make the input force less and the output force more. So they're able to put out more force for us. And they can also change the direction that a force is applied in. So if I apply a force in, it can change the direction that force is applied out. Finally, machines are never going to be 100% efficient. Okay? So efficiency is a ratio of output work to input work. Input work is the work that you do on the machine, and output work is the work the machine does on an object. So in the case of the lever and the bottle, the input work is the work that I do on the bottle opener, and the output work is the work the bottle opener does on the bottle cap. But we know that friction is a thing, and because friction is a thing, in every situation, some energy is going to be lost as heat. So 100% of the work that I put in is not always going to come out. It's always going to be at least 95 or 98% efficient, never 100%. You can calculate efficiency using the formula efficiency equals output work divided by input work times 100. So if I say my input work is, let's say 70 joules in, and my output is, let's say 60 joules, then I could calculate my efficiency by doing 60 divided by 70 and then multiplying it by 100 to get the percentage. Someone want to do that math for me? So it comes out to like 85.7%. Okay, or you could round that up to 86 if you wanted. So if I give you input in joules and output in joules, I want you to calculate the efficiency to a percentage. Okay? Questions about calculating efficiency? As we said, all machines have friction, therefore some energy is always lost, as heat and machines will never be 100% efficient. So that should be our second of our 2 disagree or agree statements that you have an answer to. All right, before we finish with notes, let's hop back over to the objectives and talk about them real quick. Objective number 1, explain what a simple machine is. Someone want to take a stab at that for me?
Simple machine is a machine that can do stuff simple.
Machines that do work using one movement.
Machines that do work using one movement. Okay? How can machines affect the direction of a force? They can change it. Good. So they can take a force that's in or down and they can push it to the sides. They can change a straight line force into circular motion. Okay, they can change the direction. How can they affect the strength of a force?
They can make it stronger.
Right, they're going to make that output force stronger than the input force that I put in. And if we come down to the next question, how do they make work easier for us? So how do they make that force, that input force, easier for us?
Less force over like a longer period of time.
Yes, less force over a longer distance. So what they're doing is they're increasing your input distance so you don't have to apply as much force. And then finally, what formula would we use to calculate efficiency?
Input force over output force times 100.
Close. It's output over input, but you're close. Output force over
Would it
input
even
times
matter?
100. Yes, it will make a difference. Because if you take 70 divided by 60, you're going to get a number greater than 100. And if you take
Yeah.
60 divided by 70, you're going to get less. So it does matter which order.
Output over input.
Output over input. Good. Okay.